Hi guys, in this video I'm going to go through the 2020 Calc Free Applications exam from last year. You can find this exam in the link below. You can also find the formula sheet in the link below as well. When using the formula sheet, you shouldn't really need to use this a lot. If you've done enough preparation for the exam, this is more just like a backup if you've forgotten anything for the non-calc section. But definitely in the calc section, you shouldn't need to use this at all. There's just a few useful formulas there if you have forgotten anything in the non-calc. Anyway, let's get started. There's only 6 questions in this exam. This section of the exam. They don't look too bad. So we'll start off with question 1. The owner of a bicycle shop recorded the type of repairs he made to bicycles with different purchase prices. So what we've got at the top there is we've got the purchase price, and on the left-hand side, we've got the type of repairs depending on the purchase price. First question was identify the explanatory variable. So when identifying the explanatory variable, you ask yourself, what's going to explain the other thing? So does the type of repair explain the bike we purchase? Or does the type of bike we purchase explain the repairs it's going to need? So in this case, obviously, you have to purchase the bike before you can repair the bike. So the purchase price is the explanatory variable because the purchase price will explain the type of repair. The type of repair won't explain what kind of bike you purchase. Well, not in this context anyway. Here it's given the percentages in each row. Now, just notice that if the explanatory variable is in the columns, so you can see that we've got the columns going down here, we would normally use column percentages to determine an association between the purchase price and type of repair, because this is categorical data. But here that's saying in each of the rows, so don't use that to lead you into answering part A. Just answer each question independently in this instance. So it says the percentages in each row of the following table show the proportion of bicycles with different purchase prices requiring the type of repair. So we're doing row percentages, and if we're doing row percentages, they should all add up to 100. The columns will not add up to 100, so don't use that either. So when answering a question like this, answer the most obvious ones first. So here in the second row, they've given us all of the information. So if that adds up to 100, 30 and 20 is 50. 100 take away 50 is 50. So that one is a free mark, basically. You're just adding up to 100. The next one I'll look at is working stuff out of a total of 60 is difficult, or it's more difficult, I would say. So the next one I'm going to do is working it out of 20, because we know that 20 times 5 is 100. So all we need to do is multiply each of these numbers by 5 to get the last row. So 3 times 5 is 15. And 2 times 5 is 10. So that's the third row completed. Now we can work on the actual harder one. It's not hard, but it's just harder. So when we're doing this one, we're just working at the percentages. So 36 out of 60. The way I would do that one there is I would say 36 out of 60. What can you divide top and bottom by to make this a nice number? So 10 is a nice number. So if we divide the bottom by 6, we can get 10. And if we divide the numerator by 6, we can have 6. And 6 out of 10 is 60. Then just using the fact that we can sum up all of them to 100, 60 and 10 is 70. And so we're missing an extra 30. I'm just going to quickly check my answer now. 18 over 60, divide both by 6 again, is 3 out of 10, which is my 30. So I know I've done that one right now. Using the information from the table in part B, so we have to use this table, describe one association between these variables. So what we're looking for in this question is there a pattern? So as we increase the purchase price, is there a specific pattern we notice? Well, we can see that just looking at the wheel and tire repairs, as we increase the purchase price, it goes down and then it goes back up. So there's not really much of an association there. With gears and brakes, it goes from 50 to 30 to 20. So it's going down and then down again. So that's an association. And then frame and suspension, it goes down and then it goes back up. So that's not really the association that they're looking for. So in this case here, one association that we can describe is that as the purchase price increases, the percentage of gear and brake repairs decreases. Because that's true for all of it. So as we increase the price or the purchase price of the bicycle, the percentage of gear and brake repairs is always decreasing. I don't know how they market in WACE. I know that this is the answer that they were looking for, but there are more associations that you could talk about, but I think you'd have to be more specific. But we'll just move on from that. A small research facility of 5 buildings with walkways represented by the edges in this network. So we've got 5 power plants. We've got power plant C, workshop E, D, A, B. The actual name isn't that important at the moment. Question A is to determine the smallest number of edges to be added to ensure that the network is connected. So connected means that it is possible for me to travel from any vertex to any other vertex in the network. So there's a path that exists between each of the vertices. So obviously we could connect E up because E is disconnected. And then we could connect up those 2 power plants via that route over there, or we could connect them up here. So there's got to be at least one way for us to travel from any vertex to any other vertex through the network. So the minimum number of edges we need in that case is 2. Complete. Complete means there exists there's an edge from every vertex to every other vertex. That means that they all have to be connected. So all we need to do is make sure that each of these is fully connected. So we can go, we've got 2, so that's an extra 1, 2, 3, 4, 5, 6, 7, 8. So we need an extra 8 edges to make that complete, because now every vertex is connected or is adjacent to every other vertex. It's got a direct connection between them. Part 3 is planar with 4 regions. So we know that when we have a connected planar graph, we can use Euler's formula. So that's the first and easiest way to do this. So we can use the formula V plus F equals E plus 2. And if you forget that formula, it is in your formula sheet up there. It's just written slightly different. So V plus F minus E equals 2. So now V is the number of vertices. Well, we have 5 vertices. F is the number of faces or regions. We want 4 of those. And that'll equal the number of edges plus 2. So 5 plus 4 is 9. And E plus 2 over there. So what number plus 2 gives us 9? We need 7 edges. But remember, we need to know the number of edges that need to be added. So we've already got 2 edges. So what we're going to do is, therefore, we need 5 edges. And that'll give us the 7 over there. That's the easiest way to do it. The only other way that I can think of to do it is to actually draw out the network. So if we draw the 5 vertices, we know those 2 are connected, those 2 are connected. The labels at this point don't really matter. And you just need to draw that by adding in edges so that you can have 5 faces. So we could go, and I'll do it in a different color here. We could go 1, 2, 3, 4, 5. So now we've got 1, 2, 3, 4 faces or 4 regions, and we had to add in an extra 5 edges. So that's the other way you can do it. So that'll be your working out for that one over there. So we need an extra 5 edges for that one. 3 different plans for completing the network with the addition of 4 walkways are shown. State which, if any, of these plans has a graph that is bipartite. So bipartite means that we can have 2 distinct groups where there are no edges connecting vertices inside the same group. So they look like these sorts of things. You could have that one there and then those 2 over there. But you'll notice that those 2 aren't adjacent to each other and those 2 aren't adjacent to each other. So the easiest way to do these ones when they give you a graph is to get out your highlighter. And I'm going to highlight C yellow. That means that C belongs to group 1. That means that B doesn't belong to group 1. So B has to go to the green group and D also has to go to the green group. If B and D are in the green group, that means that A must be in the yellow group. Now, E is its own group now because E can't go with the green group or the yellow group, so it's got to have its own group. So plan B is not bipartite. We'll do the same process for plan Q. So that one, so B can't be yellow. D can be yellow and E can be yellow, and you'll see that E will be green and A will be green because we can't have 2 connected that are the same color. So plan Q is bipartite. And then we can check plan R, but notice that it's only worth 1 mark. So if it's only worth 1 mark, there's usually only one answer that they're looking for, but just take that with a pinch of salt because it could be 1 mark for having both if there are 2, but it will just check plan R anyway, just to be safe. So C will be yellow. That means that B must be and A must be green. If B is green and A is green, that means that D must be yellow. But then again, we end up with the same situation where we have E being a different color over there. Now notice that if you can see a triangle, so if you can see a triangle forming, that means that it will not be bipartite because you'll need at least 3 colors. So shortcut, look for the triangle. If there's a triangle, it's not going to be bipartite. Okay. All right, Eulerian. Eulerian means exactly, no, not exactly, because that's semi-Eulerian. It's no odd nodes. That's how we find Eulerian graphs easily. What does Eulerian mean? It means that we can draw a trail with no edges repeated, and we start and finish at the same vertex. That's what Eulerian means. Semi-Eulerian means that we have a trail with no edges repeated, but we'll start and finish at a different vertex. So this time, Eulerian, we want no odd nodes. So let's go and count the edges. So C has got 2 edges coming out of it. B has got 2 edges. A has got 1, 2, 3. So straight away, we have 1 odd node, or at least 1 odd node, so we can stop with plan P, because it won't be Eulerian. We'll do plan Q next. So this one's got 2 edges, 2 edges. A's got 3 edges. Because it's got a degree of 3, we can stop now, because it's not going to be planar. Eulerian, sorry. C is 2, D is 3, so we can stop there. So, how many of these graphs are Eulerian? None. Let's just look at plan P quickly though. E's got 2 and D has a degree of 3. So you can see that with plan P, it has exactly 2 odd nodes, and that would mean that it's semi-Eulerian. Hamiltonian cycle. Hamiltonian means we visit each vertex exactly once. Cycle means we start and finish at the same vertex. With Hamiltonian, we don't care about going across all the edges. We just want to hit up all the vertices. With Eulerian, we care about all of the edges. So here we're just concerning ourselves with going past every vertex. So what we're going to do is we're going to see if we can draw a route. So plan P, boop, 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 boop. Yep, I've got a path that visits each vertex, and I've started and finished at the same vertex. So plan P is definitely one of them. Then let's go to C. So C, I could go to B, A, E. Oh, now I've got to go back to B. There's other ways you can try and draw it, but you won't ever be able to do a Hamiltonian cycle with plan Q. Let's try plan R. We'll start at B. We'll go to C. We'll go to A. We'll go to E. We'll go to D. And then we'll go back to B. So plan R is another one that we can draw where we visit each vertex exactly once and we start and finish at the same vertex. Yeah. And obviously, because we're not allowed to repeat a vertex, we can't really repeat edges either. Oh, not too bad. Question 3, bipartite graph below, average number of cells per day, 4 specialist price, machinery by 4 salespersons. The salespersons went through a rotation process of spending a number of full days selling only one type of machine before moving on to the next. The company that makes these machines wants to maximize. That's a keyword you need to highlight. We want to maximize something. This is an allocation problem, which means you're probably going to have to use the Hungarian algorithm. All right, complete the matrix below. So salesperson 1, 4, 5, 2, 12, 4, 5, 2, 12. Salesperson 2, 10, 4, 8, 2, 10, 4, 8, 2. So we're just reading them from left to right. So when it wants us to complete the matrix, all we need to do is read it from left to right. So salesperson 3 is 3, 4, 6, 14. And salesperson 4 is 9, 3, 5, 3. Easy mark there, just filling in blanks. All right, show the use of the Hungarian algorithm now. So now we have to use the Hungarian algorithm, and we want to maximize the sales, obviously. So when we're doing a maximum Hungarian algorithm, we need to turn all of the large numbers into small numbers and all the small numbers into large numbers. The way we do that is we pick the largest number in the matrix. So in this case, we're going to pick 14. That is the largest number in the matrix. And we're going to subtract every number from 14. So I'm just going to write down here, subtract every number from 14. That means that 14 will have a value of 0, because 14 minus 14 is 0. And when we use the Hungarian algorithm, we will minimize those. And the minimum value will actually give us the maximum value. All right, so let's just go, and I'm just going to do it up here, and I'm going to sketch it down there. So 14 minus 4 is 10, 14 minus 10 is 4, 14 minus 3 is 11, 14 minus 9 is 5, 14 minus 5 is 9, 14 minus 4 is 10, 10, 11, 12, 6, 8, 9, 2, 12, 0, 11. And what I'm going to do is I'm just going to grab this and we'll move it down. And that just goes there. All right, so that's the first thing we have to do. And now we can just go through the normal process of the Hungarian algorithm. So we'll subtract the smallest number in each row. So minus 2, take away 4. We can take away 0 there. You don't really have to do that. And we can take away 5. So when we've done that, 10 minus 2 is 8, 9 minus 2 is 7, 10, 0. 0, 6, 2, 8, 11, 10, 8, 0, and 0, 6, 4, 6. All right, we subtracted the smallest number in each row. Now we'll subtract the smallest number in each column. So the first column we don't need to do anything with. We'll subtract 6 from the second column. We'll subtract 2 from the third column, and we don't need to subtract anything from the last column. So that gives me, and I'm just going to write them in their columns now. 1, 0, 4, 0, 8, 0, 6, 2, and 0, 8, 0, 6. All right, now using the least number of lines possible, we're going to cross out all the zeros. So I can use 1, 2, 3 lines there. But we need as many lines as we do salespeople or rows or columns, because this will always be a square matrix. So what do we do now? What we're going to do is we're going to pick the smallest number that isn't crossed out. So we're going to pick the 1. And we're going to subtract 1 away from everything that doesn't have a line through it. So what do I mean by that is that all of those numbers don't have a line through it, and all of those numbers there don't have a line through it. So we're going to subtract 1 from each of those. And then we're going to add 1 to things with 2 lines through it, or basically a cross. So that's got a cross, and that's got a cross over there. So that's the next step. So what do we get? 8 minus 1 is 7. 1 minus 1 is 0. 8 minus 1 is 7. The 0 doesn't change. Those don't change, but we have to add 1 to the 8, making that 9. Then we'll have 10, 3, 5, 0, and the last one is 0, 0, 2, 7. 0, 0, 2, 7. And now we're going to cross out the zeros using as few lines as possible, and we're aiming for 4. So 1, 2, 3, 4. Now we're done. Because now we have 4 rows, we've got 4 lines. Now we need to start allocating things. And I like to pick the things that need the allocation first. So we're allocating zeros that have only 1 line through it, not 2 lines. So I'll start at the bottom down there. That's the only way I can allocate, which one is that? Salesperson 4. That is the only way to allocate that, because we can't use this 0 over here. When we go to salesperson 3, they can only have that one. Now, if salesperson has used the first machine and salesperson 3 has used the last machine, that means that I can't pick that one anymore. So the only one that salesperson 1 can do now is this one, which means that salesperson 2 has to use that one. Now we'll go and highlight those in the matrix above. So it went like this. Broop, broop, and salesperson 4 had the first one, obviously. Now, you'll notice that we've picked the 14. That was the biggest number. We wanted to maximize it. So that our answer does make sense that we have picked the biggest number. All right, so now we just need to write the allocations. They've been super nice to us. So person 1 gets B, person 2 gets C, person 3 gets D, and person 4 gets A. Now, part C is how many more sales? More sales means that how much should it go up or down by using the allocation in part B. So use your answer here to compare it to this allocation over here. So first, let's work out what our allocation was. Our allocation was 5, 8, 14, and 9. So part B was 5, 8, 14, and 9. 5 and 8 is 13. 13 and 14 is 27. 27 and 9 is 36. Now we have to work out this allocation, and it looks like it's just going along the lead diagonal, so A, B, C, and then D. So let's work out the new one. So A, B, C, D gives us 4, 4, 6, 3, because we're just looking along the lead diagonal over there. So 4, 4, 6, 3. So we're going to go 4 plus 6 plus 3. 4 and 6 is 10. 4 and 3 is 7. 10 and 7 is 17. So how many more cells? So now we have to find the difference between the two. So 36 minus 17 equals, we need 13, and 6 is 19. Now I'm just going to go and check my units. There's no units in the question. It doesn't seem so. Yep, 19 more sales. Done. All right, question 4. This looks like bipartite. The table shows data comparing the gestation period in days and the birth weight in grams for 10 Tasmanian possums. So first of all, if the gestation period is along the x-axis, this means it's the explanatory variable. And G is along the y-axis, that means that it's the response variable. So they've told us what's the explanatory, what's the response. Plot the last 5 days. So we're going to go back 1, 2, 3, 4, 5, and we're going to plot those days over there. So 42 and 41 goes over there. I'm going to make my dots nice and clear. Don't do small dots. Make sure that your dots are clear. 43 and 42. 44 and 43. 44 and 41. And 45 and 42. All right, so just looking at those dots there, they're fairly far apart. The scaling might have something to do with that, but it doesn't seem like there's a strong relationship. Yeah. The correlation coefficient for these observations is approximately negative 0.6. So 0.6 means it's a moderate relationship. It's not strong, but it's not super weak. And the negative implies that it's a negative relationship. And how else do we know that's a negative relationship? That the gradient is negative. So there's lots of clues to that the relationship will be a negative relationship. Why do they want you to plot 5 points in ATAR? I have no idea. That's a year 7 skill. Plot the last 2 maybe. No, 5 is too much. All right, describe what this correlation suggests about the general pattern of association. It's worth 2 marks. They're looking for 2 things. The first thing is going to be the strength, and the second thing is going to be the direction. So we've already said that there is a moderate negative linear association. We're saying linear because we found the line of best fit. So we just talk about strength and direction. There's a few things we can talk about here. So we could interpret the gradient. This isn't part of the question, just so you know. I'm just going to practice some stuff. So if we wanted to interpret the gradient, the standard response is for every unit, whatever the units are, increase or decrease, depending on if it's a positive or a negative. Oh no, it's always an increase, sorry. For every unit increase in x, the y, whatever y is, the y will increase or decrease, depending on if the gradient is positive or negative, by, and then whatever the gradient is. So if I was interpreting the gradient of minus 0.17, I would say for every, now the units is days, so for every extra day, the birth weight, because that's our y thing, will, and now the gradient is negative. So if the gradient's negative, we're going to use the word decrease. Decreases by, and then you just write the number 0.17. So that is your standard response for interpreting the gradient. The standard response for interpreting the y-intercept is going to be something like this. when the x value is 0, the y value, whatever that is, and then you just write down what the y-intercept is. So in this case, the y-intercept is 49. And then you just need to talk about if that makes sense or not. So in this example, we would say when the y variable is the gestation period, and the gestation period is 0 days, the birth weight is 49 grams. And then you ask yourself, does that make sense? So does it make sense that if the gestation period is 0, that the birth weight is 9? And so if it doesn't make sense, you'll just say something like, this does not make sense in the context of the question or scenario or whatever it is. So that's how you kind of tackle those types of questions. You just, whatever the x is, you just put that word in there. Whatever the y is, you put that word in there. And then you just put the numbers where they belong. So that's a standard response for something like that. So let's just get rid of all this because it's not part of our final solution. And we'll just cut it out. And we'll get rid of the bottom bit. All right. Determine the coefficient of determination. So we know that the coefficient of determination is r squared. And if r is negative 0.6, the coefficient of determination will always be positive because 2 negatives make a positive, 2 positives makes a positive. And 0.6 squared is just going to be 0.36. You could also write that as 36% if you wanted to. State the meaning of the coefficient of determination. So this is another standard response. And the standard response is in red. So what we would say is, let me just try to zoom in a bit. There we go. Whatever the percentages, variation in whatever the y variable is can be explained for by the variation in and whatever the x is. So that's your standard response. So our response would be 36% of the variation in, and our y variable was the birth weight, can be explained for by the variation in, and our x variable was the gestation period. And I'm just going to write in days there. Use the least squares line to predict the birth weight of a possum after 40 days gestation period. So we need to substitute 40 into the equation that they gave us. So G is minus 0.17 plus 49. So G is minus 0.17 D plus 49. So we need to substitute in 40. A good way to write that is just G at 40. So we're just putting 40 into there. And then instead of writing D, we would write 40 there plus 49. So I'm going to do this bit first, and I'll do it on the side here. So we've got minus 0.17. Let's ignore the negative as well. Times 40. So what I'm going to do is I'm going to times it by 10 first. So that's 1.7 times 4. And then I'm going to say 1 times 4 is 4. And 7 times 4 is 28. So that'll be 2.8. And 4 plus 2.8 is 6.8. So that's going to equal minus 6.8 plus 49. Then I'm going to do some subtraction. 49 take away 6 is 43. 43 take away 0.8 is 42.2 grams. And that's only worth 1 mark. So they're only looking for the 42.2 grams. Comment on the validity of this prediction. So there's a few things we want to talk about when we talk about the validity of a prediction. We want to talk about if we're interpolate ing, or extrapolating. So interpolating is inside the x numbers, extrapolating is outside the x numbers. Then we want to talk about the strength. And if they've given us the residual plot, or if they've given us any questions about the residuals, we can talk about the residuals. Because we know that if the residuals are not random, or if the residuals are large, that the linear is not a good fit. So in this case, they haven't mentioned residuals, so we're not going to talk about that. They've given us the strength in terms of R, and we know that we are interpolating because 40, so interpolating, we're allowed to accept anything from the first number to the last number. Anything inside this region is interpolating. Anything outside this region is extrapolating. So I'll just get rid of all of that. Here we go. So we're predicting at 40. Oops, too much. Got a bit too excited there with my eraser. We're predicting at 40. So 40, we said it was 42.2. That's well within the interpolating region. But we also need to consider the strength of the relationship. So how would I answer this? I would say that the prediction is not reliable. And then I'm going to give my reasons. So always state your answer and then give your reasons. Even though we are interpolating, if I can spell interpolating right, there is only a moderately strong association. And then in brackets, I'm going to write R equals minus 0.6. I'm just stating what the correlation is. So if you give an answer, it's worth 2 marks. Just try and show off how much you know. So we know we're interpolating, but we're also acknowledging that there's only a moderately strong association. So prediction isn't reliable. I'm not a fan when they give you questions where it's kind of on the fence a bit. Because if the correlation was minus 0.7, then I would say it's reliable, but it's really hard to answer these ones. I think as long as you justify your answer, you should get the marks for it. As long as it's not an obvious, like if it's 0.8, you can't say, or it might be reliable. If you're interpolating, it will be reliable. All right, Pudgy, is there any statistical evidence to support the research view that a higher birth weight will cause? So anytime you see the word cause, or anytime the question implies something's causing something, there is a standard response. The standard response is no. Association does not imply causation. There may be lurking or confounding variables. Because remember that when we find these associations, it's not a direct relationship. There's some association, so we've identified that there's a negative association, but we can't say that higher birth weight causes a longer gestation period or a shorter gestation period. Which is weird, the way they've written it anyway. All right, question 5. Communication Wi-Fi network is to be installed. Service shop located located 12. Shops located. Actually, let's go back to this question here. Usually we use the explanatory variable to associate it with the response variable, but yeah, they've said that the response variable causes the explanatory variable, which doesn't make sense anyway. Like, why would birth weight cause a shorter gestation period? Because you have your gestation period and then you are born. So, let's move on. Not a good question. So we've got a communication network. Numbers on edges is quoted in hundreds of dollars. So when you write your answer, make sure you write it with using hundreds of dollars instead of just units for the direct link between the vertices. Show clearly on the network the minimum spanning tree. So in the curriculum, it says you have to use Prim's algorithm. I'm going to do that one last. I like Kruskal's algorithm. It's a lot easier to use when you're finding a minimum spanning tree if you are given the network. If you're given a table, I would go with Prim's. If you're given the network, I would go with Kruskal's. Kruskal's is not technically in the course, but it is a quicker way to get a minimum spanning tree. And this is the way it works. What you do is you pick the smallest edge. So in this example here, I think the smallest one looks like 8. And then we'll pick the next smallest one. So after 8 comes 10. And you'll just keep picking the smallest edge as long as it doesn't create a loop or a cycle. So you just keep picking them as long as it doesn't create a loop or a cycle. So after 10 comes 12. We haven't created a loop or a cycle yet. We can pick another 12. Haven't created a loop or a cycle. Then we can pick 13. Still no loops or cycles. Is there a 14? I can't see a 14. I can see a 15. So we'll use that one next. Now, after 15, I could pick 16, but if I picked 16, I'd be creating this cycle, and that's what we want to avoid. We don't want any cycle, so I can't pick that 16. So after that 16, comes 18 perhaps. So I can see an 18 over here. I can see an 18 down there. Where else can we go? After 18 comes 19. So I'll pick that one. Then 21. And then 28. So you can see that we've picked every vertex now. So just double check you've picked all your vertices. And this is why it's really important to bring a highlighter in. Always bring a highlighter. At least, I'd say at least 3 different colors to your exam. All right, cool. So there it is on the network there. Determine the minimum costs. Now we just have to go and add up all those numbers. Now it's worth 2 marks, so write down all the numbers first and then add them all up. So we've got 10, 21, and 13. So I'm just going to go 10, 21, 13. And you might even want to just put a little dash through them so you don't double count. 15 and 8. We've done that one. We've done that one. Then we'll go down. So we'll go 28 and 12 plus 28 plus 12. Then we'll go 18 and 12 plus 18 plus 12. And then we'll go 18 and 19. So plus 18 plus 19. So 10 and 21 is 31, 13 and 15 and 8. We'll just get rid of that one as well. 13 and 15 is 28, 28 and 8 is 36, 28 and 12 is 40, 18 and 12 is 30, 18 and 19 is 37. All right, let's see what we've got. 3, 6, 100, 130, 160. And then we got 1, 7, 7 and 7 is 14. That's 174. So the total number of cells is going to be, or the total cost is going to be 14700. Just don't forget that the answer is in hundreds of dollars. All right, next one is due to further construction of the shopping center, edge GJ is now not feasible. Explain how this will change the solution in part A. So now GJ, which is this one over here, isn't feasible anymore. So the rest of the network works pretty good, but we need to connect up the two halves. We need to connect up the top half with the bottom half. And the only edges we have to pick from are the 34, the 32, the 33, and the 30. So out of those four, the one that we're going to pick is obviously going to be the 30. So now we're going to go from 28 to 30, and we're going to pick the edge AB. So explain how this will change the solution in part A. So how will it change the solution? Now we will use A, B instead of what was it, GJ? Yeah, GJ. And we've gone from 28 to 30. So this will increase the cost by 2, and the units were hundreds. So $200. Question 6. A small business office has 5 separate areas connected by doorways shown as gaps in this diagram. The adjacency matrix below represents the number of doorways directly between each area. So the doorways from R to W is 1, 2. The doorways from B to K is 1. Set the meaning of the 0 entries in the matrix. Well, that just means there is not a doorway between the rooms. What you'll also notice is that the lead diagonal is all zeros because there's no doors in the room leading to itself, because that doesn't make sense. And you'll also notice that the graph is symmetrical, because obviously if there's a door from B to K, there'll be a door from K to B. So straight away we can see that this is a symmetrical adjacency matrix. If an adjacency matrix is symmetrical, this is just extra information by the way, that means that the network will be undirected. Alright, determine the value of x and y. So x is W and K. So how many ways can we get from W into K? Well, there's one way. So x is 1. And then y. Well, we know that the graph is symmetrical, just an FYI. So we know that y is automatically 2. But we know that to get from R to W, there is 2 ways that we can get from R to W. So we can go this way or that way over there. There's 2 ways to think about that one there, but we just know that we've done y correctly because the adjacency matrix should be symmetrical about the lead diagonal. Describe how the total number of doorways for each area can be found from the adjacency matrix. Well, all we really need to do is we just need to add up the rows. Because remember, row 1 is how to get from B to B, B to K, B to M, B to R, B to W. So we just need to sum each row. Complete this network with vertices to the office areas. So let's check out what R is. R can go to M, and there's 2 ways for R to go to W. So we'll just add an extra edge going from R to W. M can go to R and W. So M can go to R and W. K can only go to B and W. So K can go to W, and K can also go to B, which isn't on there at the moment. Yeah, looks good. Double check that. Those 2 are connected. M can go to R and W. M can go to R and W. Yep. I'm happy with that. Right, determine how many different routes there are between the meeting room and the workspace that pass through exactly 2 doorways. So the meeting room is M and the workspace is W. So we could go from M to R and then R to W. That's one way. But there's two ways we can get from R to W. So the total number of paths is 2. Now this is only worth 1 mark, so they're only looking for the 2 there. And we'll get rid of this stuff over here. Alright, so that's the end of the calc free section. It wasn't too bad. Most of it's relatively straightforward. A lot of it's routine stuff. Obviously adding up numbers can be challenging at times. Lots of standard responses in your bivariate, so there's not too much problem solving there. Using the Hungarian algorithm, that's just a process you need to follow, so nothing too tricky there. These are just testing definitions of bipartite, Eulerian, Hamiltonian. Nothing very tricky there either, just definitions. Planing with 4 regions may have taken students more time if they didn't use Euler's formula. But you could have just drawn it as well. That might have just taken a little bit longer. The hardest question, I would say, was actually the first one, to be honest. Just interpreting and finding associations. I'd say that's one where you would have to think the most. The rest of it's pretty standard. Not too challenging. So this was the 2020 Calc Free Apps exam. In part 2, I'm going to do the 2020 Calc Assumed Apps exam. And then we'll practice using the class pad for that section. I hope you enjoyed this video, and I'll catch you next time.